Okay, so we're going to start 3.4, which is all about what's called the rational root theorem. Let's switch over here to white. So before we jump into what that is, let's do two things. One is to say, well, what is a rational? What does it mean to be? What is a rational number? Well, you have integers, which are, 0, plus or minus 1, plus or minus 2, and all of that. And then you have what's called the rationals. The rational numbers are just fractions, all fractions. So this is all integers. So this is all integers, because all integers can be written as the integers divided by 1, as well as things like, a half, or 3/7, or negative 9 over 120, so on and so forth. So what we're going to ask for is when does, or what, sorry, not when, what possible rational roots or zeros does a polynomial have? And before we answer that question, let's just do an example here. So let's take f of x to be x minus 2 times x minus 3 times x plus 4. So what are the roots of this polynomial? The roots are, well, we set f of x to be equal to 0, which means we have x minus 2 times x minus 3 times x plus 4 being equal to 0. So x equals 2, 3, or minus 4, and these are the zeros. These are called zeros or roots of f of x. Because when you plug it into f, you get 0. So, so this means f of 2, f of 3, f of negative 4, these all equal 0. Okay. If you multiply this entire polynomial out, f of x, you'll get x cubed minus x squared minus 14x plus 24. And notice that the numbers 2, 3, and negative 4 are factors. They divide evenly into factors of the number 24. And this is not a coincidence. It turns out to be a general pattern. More generally, what happens is actually the following. So when you write these as rationals, you divide these by 1, right? So these roots are actually 2 over 1, 3 over 1, and negative 4 over 1. And it turns out that the denominator, so these denominators right here, so let's label those with a different color. So these things are our denominators. They're all, in this case, equal to 1. These denominators turn out to be a factor of the lead coefficient. In this case, the lead coefficient is right here. It's 1. This is, remember, this is called the lead coefficient of this polynomial. The denominators of these fractions, they're integers, but technically speaking, they're also fractions. The denominators always end up dividing into the lead coefficient. So the denominators, in this case, they're just 1, but the denominators turn out to be factors of the lead coefficient. And the numerators here, which are to the 2, 3, and -4, these are our numerators. They turn out to be factors of the constant term, which in this case is 24. And that turns out to be actually always the case for any polynomial. And that's exactly what the rational root theorem says. So let's state the theorem now, a little bit formally. Rational root theorem. What does it say? Well, given f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus so on and so forth, a1x plus a0. What do we have? If f of p over q, so p over q is going to be our root. If f of p over q is 0, which means, i.e., p over q is a root or a 0 of f of x, then the numerator p is a factor of a sub 0, which is our constant term here. So a sub 0 is that last term, which was a 24 in our example. So p is a factor of a0, and q is a factor of the lead coefficient, which is a sub n. And that's right here in red. I'm just circling that. So q, the denominator, is a factor of a sub n. P is a factor of this constant term, a0. So what we're going to do now is we're going to go the other way. Let's say we're going to do the same example. So let's do an example. So let's take the same polynomial, x cubed minus x squared minus 14x plus 24. Now, just using the methods that we've learned in the past, we don't know how to factor this polynomial. So as of now, we cannot factor this. What we can do is use, because if we wanted to factor it, we would need to know the roots. So remember, so recall that if f of c is 0, then x minus c is a factor of f of x. This is something that we saw in the last section. If you have that f of something is 0, then x minus that is a factor of f of x. So let's now consider all possible. Let's list. So our first step here is list all possible rational roots of f of x. So how do we do that? Well, we take the number 24. And we list all the factors of it. We take all factors of 24, and those will be our possible numerators. So for example, in this case, these are the p values. So p could be plus or minus 1, right? 1 is a factor of 24. 2, and we always list both plus and the minus. 3 goes into 24. 4 goes into 24. 6 goes into 24. 8 goes into 24. And 12 goes into 24. So these are all, and of course 24 itself goes into 24. So these are all, this is the list, and it's a long list, I know, but these are all factors of 24. Okay? So our numerator for our particular situation is going to be one of these numbers, and we'll just try them out one by one. And similarly, for the denominator q, how do we list all possible denominators, well, a sub n, our lead coefficient, this was a0, a sub n, the lead coefficient was 1. We're going to list all possible factors of 1. Well, there's only 2 of them, which is plus and minus 1 itself. So these are all factors of 1, and these are all possible denominators. Okay. Now the nice thing about, so what we're going to list now is what are the possible roots. So the possible roots are, well, it's each possible p-value divided by each possible q-value. So for example, in this case, I'm going to list it right now very in detail, but it'll shrink down to a little bit simpler situation. So we have positive 1 over 1. So p over q can be 1 over 1, 1 over negative 1, negative 1 over 1, negative 1 over negative 1, 2 over 1, 2 over negative 1, negative 2 over 1, negative 2 over negative 1. I'm just taking each p-value. So this is for p equals 1. Here p equals negative 1. Here p equals 2, and so on. You can see already there's a bunch of redundancies, like this one equals 1. This one also equals 1. I'm just, for the first time at least, I'm writing down some things explicitly. So 3 over 1, 3 over negative 1. This is when p equals 3. And you can go on and on and on. But at the end of it all, since you're just dividing by 1, it's basically you end up with just the exact same as the set of p-values itself. Because remember, when you're dividing by 1, you're not changing the number. And when you're dividing by negative 1, you're just negating it, so you still get plus and minus each particular number. So the p over q values, because q was just plus and minus 1, right? Those were the possible values of q. You end up with just the possible p-values. So plus or minus 8, plus or minus 12, plus or minus 24. These are the possible, so this set right here, this set, these are all possible rational roots of, and let me just rewrite the polynomial because that got left behind, of f of x, which was x cubed minus x squared minus 14x plus 24. Okay, so what we do, well, if we didn't know any better, which at this point we don't, we just try each one out. So we're going to try f of 1, we're going to try f of negative 1, we're going to try f of 2, and negative 2. And of course, if we didn't find any of them that worked till then, we would keep going, but we will find one that works soon enough. So f of 1, well, what is that? That's 1 minus 1 minus 14 plus 24. That's not 0. So we move on to the next one. What's f of negative 1? That's negative 1 minus 1 plus 14 plus 24. That's not 0 either. What about f of 2? 2 cubed is 8 minus 4 minus 2 times 14 is 28 plus 24. And what do we have here? Well, 8 minus 4 is 4. 4 minus 28 is minus 24 plus 24. This does give me 0. So this one is a root. So we know now that 2, so I'm not going to go on to the next one because we found one that worked. The moment you find one that works, you stop. So 2 is a root of f of x, which means from the previous section that x minus 2 is a factor of f of x. So we now have completed stage 1 of this process of finding a root. And our goal here, remember our goal was to factor this. Goal was to factor f of x. Okay. So how do we proceed? Well, we don't want to just keep going because we have so many possible values. We can actually use this information. Remember now, we can do synthetic division. We're gonna take f of x, which is x cubed minus x squared minus 14x plus 24, and divide it by x minus 2. And we're going to use synthetic division. So we take 2, we write down the coefficients here of f of x, we drop down the 1, we multiply 2 times 1 is 2, we add here, we get 1, multiply the 2 times 1, you get 2, you get minus 12, 2 times minus 12 is minus 24, and indeed you get the remainder 0. Of course, you should get the remainder 0 because x minus 2 is a factor. So recall here that remainder is 0, and this must be the case. If you didn't get r equals 0 here, then something is wrong. So what do we get now? Well, think of this as d of x is x minus 2, and we want to write f of x is equal to d of x times the quotient q of x plus the remainder, but the remainder is 0. So you just get f of x equaling d of x times q of x. So d of x here is x minus 2. What is q of x? Well, let's recall how to do this. This was the x cubed term. This was the x squared term, x term, and constant for f. This thing here is what defines q, where this is the x squared term, this is the x term, this is the constant term. So what we have here now is x squared plus x minus 12. Well, so there are two options now. We want to factor f completely. We've done a partial factorization. Sometimes you can just directly factor this. So you have two options now, directly factor, or sometimes you need to use the rational root theorem again. Or in other cases, if it doesn't work out, you may also just use the quadratic formula. And that generally is a good method, especially because it works no matter what quadratic polynomial you have. What we're going to do is, in this particular case, let's check if this directly factors. We need two numbers that multiply to negative 12 and that add up to 1. And that actually, we can find that because this is x minus 2. And then x squared plus x minus 12, the numbers 4 and 3. So if you have x plus 4, x minus 3, then this piece is exactly that, because 4 times minus 3 is minus 12. 4 plus minus 3 is positive 1. So this actually factors now, and this is your final answer. Okay. So what I'm going to do is I'm going to start you guys off on an exercise here, and I'm going to leave you to finish it. So I'll start it off. So the exercise is we're going to do the same process for this particular function, 2x cubed plus x squared minus 13x plus 6. And our goal again is to factor f of x. And so what we do is we want to list all possible rational roots. So what do we get here? Well, our numerators are factors of 6, which is our constant term right here. And our denominators, q, are factors of the number 2. So, and 2 is our lead coefficient right there. So what are the factors of 6? We get plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. What are the factors of 2? Plus or minus 1, plus or minus 2. So P over Q overall, which is going to be our list of actual possible roots, this is going to be plus or minus 1 over plus or minus 1, plus or minus 2 over plus or minus 1. And notice these just overall give you plus or minus 1. When you're dividing by 1, you just remain with whatever integers you had originally. So plus or minus 1, plus or minus 2, plus or minus 6 over plus or minus 1. So you divide all the p's by plus or minus 1, you just get the list of the original p-values that you started off with. What changes is when we divide by 2. So let's now take each p-value, I'll do this a little bit slower here, take each p-value and divide it by plus or minus 2. So let's write those down, and I'll write those in red. Well, what else do we have? We have plus or minus 1 divided by plus or minus 2. We have plus or minus 2 divided by plus or minus 2. Plus or minus 3 divided by plus or minus 2. Plus or minus 6 divided by plus or minus 2. So what do those red values come out to be? Well, this thing is just plus or minus a half. Okay? Because you have a half and it's either going to be plus or minus. 2 over 2, well, that's plus or minus 1, and that's already been listed. So we skip that one because that's redundant. What about plus or minus 3 over 2? Well, yeah, that's a new one. 3 halves is a new value, so plus or minus 3 halves. And plus or minus 6 over 2, well, that guy is 6 over 2 is 3, so that's the same as plus or minus 3. So overall, your list is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus a half, and plus or minus 3 halves. That's your list of possible rational roots. So what you're going to do now is go ahead and try these out. Start with the integer values. So plug in, find f of 1, f of minus 1, f of 2, f of minus 2, and so on. And once you get a value that works, so once you get a value so that f of that number is equal to 0, you're going to do synthetic division. And then you'll factor further. Okay? We'll do this exercise in completion in the next video. For now, we'll stop here, and we'll continue next time.